All right. So in the last series of videos, we were introduced to this concept of the SIR models. So an SIR model is basically a way to model the spread of a disease in a population. And normally when we used to count how one number changes over time, here we keep track of how three different numbers change. So we have percentage susceptible, percentage infected, and percentage recovered from a given disease. So the percentage recovered is proportional to the percentage infected, because in order to recover, you have to first be infected. So the recovered number is a portion of the infected, and so if we say I is infected, then to get recovered, then it's infected times a certain rate. And then to get infected, well, the number of people infected is going to be related to how many people there are susceptible. The more people that are susceptible, the more people can be infected. But as the number of people who are susceptible goes down, the number of people who can get infected also goes down. So the infected is proportional to is related to both the number of currently infected and currently susceptible. So we have infected, susceptible, and also a infection rate, which is A. And then so if we want to figure out how these how these different numbers change. What is the rate of change for susceptible, rate of change for infected, rate of change for recovered? That's all related to these proportions that we generated. So the change in susceptible over time is the A times IS, but since over time the number of people susceptible goes down as more people get infected, more people recover, the original pool of susceptible goes down. So that's why there's a negative. And then the change in infected is basically the amount that got infected, and then minus the amount that recovered. So AIS is the amount that got infected, and then of those that get infected, a certain amount recover. So that amount that recovers is BI. So you have AIS minus BI, and then the change in the number of people who get who eventually recover, that's just going to be BI, and it's positive because the number of people who recovered is just going to go up over time. Now, other complexities obviously exist when we have to model something so as complex as like the effect of a disease in a population. Like one of these complexities could be like those who are there can be people who get infected but they don't show any symptoms, and there's also people who are immune to the disease or somehow gain immunity to the disease during the course of the spread, and all of these can alter the numbers we have here. And then kind of like what Alex pointed out earlier, this doesn't really account for the number of people who actually die from the disease. So that's also something that that's also like a complexity that we're not accounting for. But the fundamental idea is that this is the base model. So with this, we can just simply build off of it and add more things that we should perhaps take into account. And then so again, A is the infection rate, and here for susceptible it's negative, since the number of people who are susceptible to infection decreases over time. And then B is the recovery rate, and it's positive because the number of people who eventually recover is going to just go up over time. So so when it comes to how this actually looks on a graph, if, for example, so this is how it would. This is the general idea of how it would look. So the number of people susceptible is a downward slope, so it's just going to keep going down, and eventually it's going to approach zero because most of the population eventually gets infected or recovers, but those that are susceptible is going to go down because everyone is going to go into the different phases. The number of people who are infected, that's going to go up to a certain point, and then it's just going to, it's kind of like a bell curve. It's going to go up, and then eventually it's going to curve and go down as over time people are going to recover. So the people who, those that are infected is eventually going to drop. And then the recovery is just going to be a straight upward slope. We start out with a few people who have recovered, and then over time, more and more people recover. And so, if we look at some of the extreme cases, so if the infection rate is really, really low, if A is really low, then the S curve will never approach 0, because not everyone, since the infection rate is so low, not only a fraction of the population, only a portion of the population will ever even get infected. So those that are the number of people who are susceptible is always going to remain relatively high. And then the other extreme is if recovery rate is really high, then we're eventually shift everything sort of leftwards. So everything just kind of happens faster. And also an important thing is that so recovery is going to go up really much faster than before, which causes, and because of that, it causes the infection curve to decrease, since at any given time, the number of people who are infected is relatively low compared to those who have recovered, since most people will recover really fast.
I have a question.
Yeah.
Could you like reiterate like what the S curve means exactly, what it actually represents?
The S curve?
Yes.
So you're going to have an initial population of people, right? And
Right.
we can say, so if there is a disease introduced to this population, then all of the initial population is susceptible to infection.
Right.
But as people get infected, that number that it was originally, that big number of people who are susceptible, that goes down because they are already infected. You know, just like if there's 100 people, and if there's 100 people in the beginning and there's a disease, 100 people are susceptible. But if 50
Gotcha.
people get the disease, only 50 people are susceptible now.
Gotcha. Okay. Thank
So
you.
that's like 50% of the original population becomes susceptible. So the percentage of people who are susceptible goes down over time.
Okay. Thank you.
Yep. Anything else? All right. Sounds like we're good.